an ITC reception where one person came dressed up very nicely, and he was clearly distinct from the crowd. And I said that he saw the image. But Shep, I must tell you that he did not surrender to any pressure. He did not really release any information about the image.
This is why I'm wearing a sidearm these days.
But we know that the data is amazing, and that we look forward to seeing the shadow at some point. So
on this subject, our first speaker today is Kazu Akiyama, who received his PhD from Tokyo University in 2015, and he's currently a Jansky Fellow at MIT Haystack Observatory. He's also affiliated with the BHI, and he's a very important contributor to the EHT project, Horizon Telescope. So Kazu will tell us today about what we are soon to, where are we soon to get with the EHT, about imaging the shadow of M87.
Right, okay, hello everyone. My name is Kazu Akiyama. I'm a postdoc at MIT Haystack Observatory, and actually I'm a PHI, well, affiliate of PHI, and I'm here, I think actually regularly. We'd be sometimes more than, actually spending your time more than Haystack. The Black Hole Initiative is the central, actually one of the central institutions for the Event Horizon Telescope project. I think you already heard of this exciting project. This is a planet-wide project aiming to take the first picture of the black holes on scales of its event horizon. So, as Jeff already mentioned, we cannot show any preliminary stuff. Well, otherwise I will be fired from that. Yeah. Well, so I actually instead want to make a kind of near-time forecast, actually what we can expect from the EHT observations happening in the last year and also this year and maybe in the next few years. The last week, when Barbara asked me for a title and abstract for this talk, I just quickly Googled Event Horizon Telescope with Milky Way at Sagittarius star, 1 hour, 2 planet target. That actually provides more than a couple of 10,000 news articles. And again, I Googled again with M87, which is another super important target to image the structure on Event Horizon scales. Then I got just only 1,000 of news articles. So I was so shocked that M87 is also another interesting source, but it's less popular. So that's why I decided to concentrate on another important target, M87, for the Event Horizon Telescope. So just quick introduction. So M87 is actually a very important source to study, for instance, the typical black hole system, system with a relativistic jet. M87 was the source with the relativistic jet discovered in 100 years ago, which was actually the first source for the relativistic jet. As you can see, probably we can expect to see a shadow of the black hole and some structure, on event horizon scales, which means actually we can study a lot of things of the black hole systems from the event horizon scales and to beyond actually their host galaxy, like a 10 to the 7 Schwarz radii.
One question about this image. Mm-hmm. How do you know where the black hole is? Because we don't know if this is a counter jet. That's actually a good question. And actually, I will not present a slide about that, but just quickly. So this jet is is a synchrotron emission from the magnetized plasma, and we actually know that the brightest point is optically thick, and the opacity of the jet is actually depending on the observational frequencies. So one thing we can do is actually we can measure the absolute position of the jet at the multi frequencies. And what we can expect is if we go to the farther deeper region of the jet, and we can expect more electron density and more magnetic field, which provide a higher opacity. So basically, we can expect that some positional shift of the black hole as a function of frequency. And actually,
it could be in the dark region.
yeah. So the good thing is the origin of the jet phase at each frequency was actually showing the frequency dependence, and the convergence of the root of the jet is actually just within this emission region. So our expectation is of course there could be a slight offset from the brightest point of the jet, a lower frequency and the actual black hole position, but it's very, very small.
Like a rotation that
Is it based on theory? I'm trying to understand. Is it based on theory or observation?
Observation.
position versus frequency.
Yeah.
The bright spot, which converges at high frequencies.
Yeah, and it's really close. I'm not sure that specific observation, but I will show some data here later. Right. So I'm not sure actually how EHT is famous here, but I start from just quick introduction about actually what is the EHT, and also what is actually this dark silhouette in this image. Then I will move on more details about M87. So what I show in the first figure is maybe we can see some dark silhouette of the black hole in this image. And here's the black hole initiative. So I think everyone knows about the black hole. Black hole is characterized by its event horizon. That is the surface of lowest scale photons, or more theory speaking, that's a singularity surface of our spacetime. So by definition, we cannot see the event horizon. But still, Einstein general relativity actually expect that if there is a black hole and if there is a photons emission near the black hole, then black hole casts its shadow in the distant observers. So here's actually one beautiful schematic view. So here's the black hole, and each lines are showing the photon trajectory along with the geodesy line from distant observers. If the impact parameter of the trajectory is large enough, then it's just slightly bended by different density effect. But actually, there is some threshold for the photon trajectory that where inside all photon trajectory will cross the event horizon. So if we inverse that photon trajectory, then the dark nature around the event horizon may cast a shadow to the distant observers. And its diameter is a 5.2 Schwarz radii, and where 1 Schwarz radii is the size of the event horizon for most people black hole. This actually doesn't change even the black hole will rotate a lot. This is again another schematic view for spinning black hole cases. And as you know, the size of the event horizon is actually smaller for spinning black hole. But we can expect actually stronger gravitational lensing effect, and that actually result in a very similar size of 4.8 Schwarz radii, even for the minimum cases. So this is just the size of the photon trajectory on the equatorial plane. So here is actually one-dimensional or two-dimensional view of from the equatorial plane. So basically, we can expect this kind of completely circular shadow for non-spinning black hole case. If the black hole has a spin, then the shape is slightly deviated from the circle. But the important thing is the diameter of the shadow is only actually something around 5 Schwarz radii, regardless of the spin and inclination angles. That change is only just by 4%, by some parameters like spin or viewing angles. So if we wanted to see, if we wanted to resolve the shadow, actually we need to resolve something at actually 5 Schwarz radii. So I would say that the most important thing to see a shadow is actually one of the key factors is the angular size of this 5 Schwarz radii. So here is a well-known black holes with a very large angular size. So the largest one, as far as we know, is the Sagittarius star, our galactic center. That is the nearest supermassive black hole with 4 million solar masses, which is well determined with the stellar orbit around the black holes. And of course, this is inside our galaxy, so it's very close, and 8 kiloparsec from us, and that provides 10 microarcsecond for 1 Schwarz radii. And another excellent target is actually M87, what I want to focus on today. So I will talk about this in more details later, but we have M87 probably have 3 to 6 billion solar masses of black hole masses, which is 1,000 times heavier than Sagittarius star. And the distance of M87 is somewhat actually 1,000 times farther than Sagittarius star. So it's all cancelled, and we have a very similar angular size of say 4 to 7 microarcsecond. So I will talk this is probably the final part of my talk, but there are some other sources that is slightly smaller than Sagittarius star and M87, like a Sombler galaxy, which it still provide a few microarcsecond for Schwarz radii. But in the current technologies, I think what we can do imaging the shadow is we can resolve the shadows at Sagittarius star and M87.
Is that model for the next biggest after the 2 primary targets?
It's actually, in terms of the angular size of a black hole, actually there are the black holes with a similar angular size. I will discuss later, but so as far as we know, another factor is we can see, we can actually detect radio waves from the vicinity of the black hole. That also actually an additional factor, and as far as I know, actually Sombrero is probably next biggest target.
Because why don't we observe this Sombrero galaxy?
Yeah, yeah, that's actually what I want to show today. Right, right. So another important thing is even if we resolve that tiny scales. Of course, there should be some good range of frequencies to see the black hole. So for M87 Sagittarius star, we have a very similar solutions. Here I just picked up the spectrum of Sagittarius star at radio wavelengths. So here is the frequency versus flux. So both Sagittarius star and M87 are brightened up by the synchrotron emission. A radio wavelengths that is coming from magnetized plasma. And basically the spectrum of both M87 and Sagittarius star have this kind of inverted spectrum. Still there are discussion where is the origin of this emission, but the general consensus for this spectrum is that the always actually spectrum is going up lower frequency, which is coming from optically thick emission, which means not transparent. And if we go, there is a peak, something around here, around 100 gigahertz, and it's actually shifted to the steep spectrum, which is an optically thin part of synchrotron emission. So what we can expect is, so at lower frequencies, everything is just optically thick and just not transparent, so we cannot see anything, just other than formula plasma. But if we go higher frequencies, and everything will start to be optically thin and more transparent, and hopefully we can see this kind of shadow. So in our current knowledge, actually, what we need is resolving something like so a few tens of microarcsecond, which is corresponding to a few times and a few Schwarz radii for Sagittarius star and M87. And also observing at high frequency enough to see the black hole. So this is actually what we did, what we have been doing with the Event Horizon Telescope. The EHT is consisting of a number of illuminator telescopes in this planet, and basically using all of them, we can make an imaginary telescope with the size of this planet. And that provides a really high angular resolution of 50 to 20 microarcsecond at 1.3 millimeter, which is where we can expect that the black hole is somewhat transparent. So then EHT resolution is expected to be enough to resolve this shadow for Sagittarius star and for M87. So I think actually, I have been here for a while, and I saw actually many talks about Sagittarius star, but actually not so many for M87. So that's why I would like to actually focus on M87. So
I think M87 is best known, and also because that is in another galaxy. So basically, we have a lot of uncertainties. For instance, for the diameter of the shadow. So in the next slide, about a couple of slides, I will show how we can expect this size of the black holes, and then move on what we learned from the REHD observations, and actually make a forecast based on our best knowledge for the size of diameter and what we learned from the EHD observations. This is my plan for today's talk. So basically, this shadow size should be something like 5 Schwarz radii. And the Schwarz radii is solely depending on the black hole mass, and angular size is just depending on distance to the M87. So to learn and to compute or to estimate the expected size of diameter, actually the important parameters is the mass and distance. So let me just go through how we measured an M87 distance in the previous literature. So this is actually a nice figure in the Wikipedia for extragalactic distance ladder. I mean to method the distance to the extragalaxies. So the vertical axis is just showing the distance to the galaxies from kiloparsec, 10, 100 megaparsec, and 100 megaparsec. There are a bunch of techniques, and basically, of course, if the galaxy is closer, then we have many more accurate options. So the redshift of the M87 actually suggests that it should be something like a 20 megaparsec. So M87 is in this range. In this range, fortunately, we have a lot of accurate method here. So first of all, in M87 we can actually resolve the population of red giant bunch. So basically, spectrum of the red giant bunch actually provide a really accurate distance measurement, which is not using some other probes. So actually, we have a primary candle for the distance using a tip of the red giant bunch method, and also we also have a sort of secondary candle, which can be considered as somewhat similar for many types of galaxies. For instance, the luminosity function of the globular cluster, and also luminosity function of planetary nebula. We also have an M87 is an elliptical galaxy, which is actually well known, which has more simple dynamics than the spiral galaxies. So for elliptical galaxy, there is a technique so-called the surface brightness fluctuations, which is basically measuring the fluctuation of the surface brightness, which is reflecting the distribution of stars. That is actually well known for the elliptical galaxies, and by just measuring the fluctuation of the surface brightness of the host galaxy, we can also actually measure the distance of the M87. So all these techniques are kind of primary or secondary method to measure distance. So a good thing for M87 is we know the distance to the M87 in several independent methods. So this is actually our best knowledge for the distance to the M87. So here I just picked up the primary method like a TLGV, another secondary accurate method like planetary nebulae, luminosity function, or other techniques. And basically, good thing is all independent distance measurement are well consistent. So basically, in our current best knowledge, it's a 6.8 megaparsec, so like something like a 70 megaparsec, and error is really small. For distance measurement, it's good to know that actually we have really good consistencies, and by accumulating many distance measurement, we can actually know it's accurate distance. So
Can I ask a question about that?
Yes.
Those functions, it looks like they're all Gaussian.
Yeah.
So you just take the plus and minus and assume
Yeah.
normal distribution?
Here I just use the Gaussian, but it's actually the likelihood function is very Gaussian-like. So it's not so actually bad. It's actually a good approximation for the likelihood distributions. And so the tricky part is actually mass of M87. So here just I list up actually a bunch of approaches to measure the mass of the supermassive black hole in the center of the galaxies. Actually, we have a lot of options depending on distance or property of sources. The most actually direct way is actually measuring time and spatial domain orbit of the stars moving around the black hole. That is very famous for Saturday star. And for distant galaxies, like actually M87. So other option is basically we cannot resolve the orbit timely. So other option is actually measuring the population of star in two-dimensional images, and also getting the radial velocity information using some spectrum from the stars. That actually is so-called stellar dynamical models. And another approach is maybe not using stars, but using some emission lines in the nucleus ionized gas. That is so-called a gas dynamical approach. And although there's another class of gas dynamical approaches, so-called mega maser method, which is very actually special for galaxies that have actually very strong maser emissions. So basically these approaches so-called actually primary method, which actually using the information of the kinematics of the gas or stars inside the surface, the radii of the gravitational influence of the black holes. So some other method for more distance of actually galaxies, some secondary methods are available, like liberation mapping or single epoch spectral observation using the empirical law from the reverberation mapping. So for Saturday star, we clearly resolve timely and spatially resolve the many orbit of stars. This actually provides independent measurement of the mass and also distance. But for other actually primary method, basically what they are doing is actually just modeling the gravitational potential of the central nucleus regions, and that actually requires some scaling factor for the physical distance at the center. So this actually this is not independent with distance measurement, and it always require assumption for the distance to convert the mass to distance ratio derived from these techniques. So this actually approach basically measure the mass to distance ratio for the black hole, and then if we know a good distance measurement, then we can actually measure the mass. So
you don't need the mass; you just need the mass to distance, right?
Yeah. For EHT, it's fine. Yeah. So for M87, actually both two approaches are available. Unfortunately, we don't have a maser in M87. And so for M87, basically the sphere of the gravitational influence can be actually resolved. So we actually can probe the gas and stellar, and that actually provides a mass to distance ratio. And also, of course, this is because the mass is just slightly proportional to the size of the Manchur's radii. So this actually provides angular size of Manchur's radii. So I just want to make a caution that if you look at many papers on the M87, actually some papers actually just using the mass from this mass to distance ratio measurement, assuming some distance, and adopting another distance to compute something. I saw actually many papers for the M87 in the dust literature. So if you look at some theory paper or observational paper about M87, you should be very, very careful about this stuff.
But the distance you said is known quite well, no? With a good accuracy. So
yeah. So for instance, our current best knowledge is something like 6.8, but previous measurement for the mass measurement adopting, for example, something like 18, something close to 18 megaparsec, and I saw many literature that it's using mass for 80 megaparsec, but using distance of 6.8 megaparsec, which is completely changed many things. So the problem for the mass is actually mass measurement of measurement of the black hole mass for the supermassive objects is still controversial. So this is not only the case for the M87. So there are actually two good approaches, which is resolving kinematics of the gas and stellar, inside something like a bony radii, gravitational inference. But the problem is, always, in many sources, the gas dynamical measurement and stellar dynamical measurement provide different the linear scales. So for instance, for the gas dynamical measurement, actually it's expected one stretch radii of the 4.1 microarc second, and the stellar dynamical is always predicting higher value. This is same for the last couple of decades. Even if the recent high quality measurement with Hubble Space Telescope or ground AO based observations, still we have these degeneracies. So so the angular size, say, is probably the lowest lower limit is something like 3 microarc second for one stretch radii currently, and it's actually the largest limit is sometimes actually beyond the expected size of Saturday stuff. But anyway, we have the large uncertainties for the angular size of the one stretch radii. This is probably good. Once we have, if we actually have an image of the shadow, then basically, if we have the image of the shadow, then we can actually determine this angular size with a much better accuracy. So there are actually many contexts. For what's the benefit to see the shadow, but actually for astrophysics or astronomy, it's definitely one of the topics is that actually we can calibrate many actually black hole measurement method with the M87. So I think it's good, and I just want to show actually how this will affect the mass. So basically, here is the horizontal axis is the black hole mass, and the vertical axis is the distance. So if we actually couple with different independent measurement for linear scales, angular size, and then also the distance, basically we can also compute what is the our best likelihood for the mass and distance, which is somewhat two-dimensional. So basically, because these contour lines is showing the contour line for the angular size, and this is almost actually parallel to the distance. So basically for mass, of course, the critical factor is this angular size. So another thing is once we can actually determine the angular size of the black hole, then that actually provides a really also tight constraint of the black hole mass. And M87 is actually one of the highest black hole mass in the current Mauritian radiation. So I think that's also actually really good for the calibration. So what actually we have learned for the M87 with the REHT observations. So REHT is very small compared to the current EHT. We have only 3 stations we have only stations in Mount Care and West Coast in US. So we have only 3 stations, which is actually poor as a layer interferometer, and can actually sample a limited information of the structure. But actually we have learned so far is still very interesting. So this is actually the published data for the M87, which is coming from Shep's paper and my actually PhD thesis work. So here the horizontal axis. Let me explain actually what radio interferometer observes. So a radio interferometer is not a simple instrument like taking a picture with digital camera or something. It's actually measuring the structure in the Fourier domain. So here actually what I'm showing is a magnitude of the Fourier component of the image of the M87 as a function of spatial frequencies. So this actually suggesting something interesting. So if we do not resolve something, so if we are looking at some point-like sources, then the Fourier transform of point source is just constant function. So if we do not see anything other than just point source, we will see this kind of just flat line. But what we will see is something that the Fourier component actually fainter for higher frequencies, which means actually we will resolve actually something. If we measure characteristic size of this structure, this actually provides 40 microarcsecond, which is something like 5 Schwarz radii for the high mass case, and for low mass case it's like a 9 Schwarz radii. So we actually resolve something really compact, very comparable to this actually size of the black hole shadow. So this actually how this size looks like in the context of M87 observations. So here I want to show is so in the horizontal axis, okay, it's maybe too tiny for people in the background, but so the horizontal axis is the distance from the black hole. Here is event horizon, and this is log scale. This is 1, 10, 100, 1,000. So 10 to the 5, and here's a bonded radii of 7. And vertical axis showing the radii of the jet. So M87 have a very prominent jet on a very very broad range of the scales. And what we can measure is so as I actually said in the beginning of the talk, actually we can measure relative location of the jet at different frequencies. So basically using that actually frequency shifting information, we can also actually put the jet in the accurate position, and also we can actually measure the width of the jet. So M87 jet have a very beautiful parabolic profile. The parallel here is like following at 1.6, so it's very close to the parabola. And basically the UHT point is coming here. So first of all, it's actually not highly affected by the factor of 2 in the black hole mass measurement. It's just shifted in these directions. But anyway, so we detect actually for something really consistent with the profile, collimating profile of the jet. So what I'm quite sure is we're resolving something very close to the jet base near the black hole, and its location is already actually consistent with the black hole location. So far, what we learned is, well, we can expect the shadow size of few tens of microarcsecond, and we actually resolve something very similar. But actually, the REHT observation is not enough to see the image of the shadows. So that's why actually we are expanding the EHT, involving many stations. So finally, in the last year, we have the first full array observations for M87 and also Sagittarius star. That involves the previous array is something like this, but now it's expanded to the planet-wide, and hopefully we will see we are actually enough. Hopefully we have enough data to image the data. So it's actually still data reaction or imaging is ongoing, so I cannot show any images, but let me make some forecasts for the future EHT observations. So actually what happening here at BHI and CFA and Greater Boston area is actually active development of the imaging techniques. I actually don't want to go details here, but actually there are many techniques developed here to robustly image this UHD data, just from the very robust data set, not affecting, not actually affected by some errors of the calculations. There are many techniques. For example, techniques developed here by Andrew Shao, myself also, actually developing new imaging techniques, so-called sparse modeling or compressed sensing. And also Katie Bauman here is also actually developing new techniques using machine learning approach. All of the techniques actually ensure that probably if we have the data set in 2017, then actually we can make images like that. So I just want to make a quick forecast actually for what we can expect. So this is very optimistic case. I mean, we have the high mass black hole, and if and in that case, we have a actually larger shadow, and actually EHT 2070-ish simulation actually provide that probably we can actually do imaging in the shadow. So for robust cases, actually, well, still actually theory work have difficulties to explain everything for robust cases. This image is the best fit for the robust, but it's still actually much less consistent with the EHT data compared to the Hymas model. So
You mean the prior EHT data?
yes. So far in theory field, I think vast majority of GIMG model prefer Hymas. But anyway, if we think about the worst case, then we have very small shadow, but still actually 2070-ish coverage is enough to see a shadow. So I'm quite optimistic about the M87 results, which I cannot show today. Maybe there is a criticism that Roma's case is not consistent with the EHT data, so then we unreasonable models. So what we can do is using a lot of models, parameterized model for the shadow, by changing offset or diameter of the emission lesions. So I just pick up actually some images, consistent with our EHT observation with various diameters. So 35 is high mass cases, which actually we can do a whole imaging. For smaller shadow, it's okay. 25, it's okay. 20 is some sort of actually best bet for the low mass cases, which still fine. 50 microarcsine, which is coming from diameter of the much radius equals to 3 microarcsine, which is the current lower limit of the measurement, is still actually we can see as a shadow. So what I actually want to make a point here is probably the large uncertainty in the linear scale is not the issue for the M87.
Why it's anti-symmetric? Why it's not symmetric?
I see. So is your question is why the images looks symmetric?
Yeah, in all of them it's very not.
Yeah. So that is a really good point. Still, actually, we are not sure on which direction images have asymmetry. That is still under debate. But regardless of the origin of emission, we can expect this sort of asymmetry. So for this case, for this model, so this model is actually expecting that there is a very light counterjet emission, which is going to another direction to the observer. But because that emission region is really close to the black hole, so all of the many photons from the counterjet, it's just gravitational lens and coming here. In that case, the emission expected images highly depend on, for instance, the co-rotation of the space-time with the black hole spin. And this actually for this image, this side is actually corresponding to the approaching side of the black hole spin. So one side is Doppler enhanced, and then another side is Doppler faded with relativistic effect. Even for accretion flow model, we can expect this sort of asymmetry because of the very high velocity of the accretion flow in the black hole. In another case, maybe so in this model, jet is oriented in this direction, and maybe forwarding jet is brighter. In that case, the emission is something here is brighter and another side is fainter. So still direction is not, it's highly dependent on actually where is actually the brightest region in the black hole. But we can accept this sort of asymmetry. Right. Okay. So sorry, I'm really pushing time, but well, I'm actually kind of optimistic person in the collaboration, but I actually my forecast for the M87 is very promising, regardless of the black hole spin. So in the final actually couple of minutes, may I? Okay. Let me actually make more long-term forecast. Okay. So far we have only two primary targets, like M87 and Saturday star. And one of the interesting questions is, are these sources only two targets? I would say probably we can increase actually number of sources that we can image the event horizon scale structure. So here, what I listed up is the known distribution of the black hole mass versus the distance for the nearby extra galaxies. So here I just plot, more than 200 of black holes, of which mass is measured by a very accurate method like stellar or gas dynamical megamasers or evaluation mapping. And in this plot, so this is log scale, and basically the contour for the angular size is just linear. And so this is showing basically the size of the one-shot radii, and every descent is here. So you can realize that actually it's not radio bright here. I forgot the name of source, but it's not radio bright. But actually, in terms of the black hole mass, actually there are a lot of sources that have a really good linear scale. So for instance, sombrero that I mentioned, which is radio bright.
Where's J star? J star, that little dot on the left.
Sorry, Sagittarius star is a kiloparsec, so it's something like here.
So it's on a straight line.
Yeah, it's just focusing on extragalactic. Sagittarius star is inside our galaxy, so it's just out of range of this one.
So anything is anything on that line? It's the same size in the sky.
That's right. That's right. So sombrero is here. The famous, wave order association like M81 or SENA is here. And another interesting target, M84, which is very close to the M87, is here, which is very well known radio galaxies. So let me just count up the number of black holes. About the black holes, and so far we have 22 black holes. If we go and further, 10 times smaller scale regions, then we have actually 90 more. Nearly 100 black holes so far. So my actually view.
Sorry, the 22 black holes are what? The ones above that line?
Yeah, above one. So I think actually the key point here is, if you want to hunt other black holes, then I think the key issue is the angular resolution. That is the most key factor. Once we can achieve, say factor of 10 actually finer scales, then we can actually increase the number of subjects. This is my expectation. So one way, maybe in future, one way to increase the angular resolution is just putting telescopes outside the Earth. That actually make EHD bigger, and we can achieve higher angular resolutions. Let me think about actually putting a telescope in space. Of course, the most important thing is what kind of orbit. Okay, hold on, please. So what kind of orbit we will need? I'll skip many things here, but basically, for instance, maybe we can put the telescope in something in the region where we have a GPS satellite, like a mid-Earth orbit or geosatellite orbit. Let me skip this. So here, just let me show actually what is, what we can expect for instance, sombrero. Here, I put just shadow image with expected angular size with the expected radio fluxes of the sombrero galaxy, and for it is actually too small for the ground EHD, but just adding 1 or 2 telescopes in the space, actually we can resolve this, for instance, the other shadow in other galaxies. So that means actually we can increase sample that we can see event horizon scale structures.
That's with the higher Earth orbit. Or lower Earth orbit. Higher Earth orbit.
Yes. Higher Earth orbit. So just do quick simulations. What we can do with something a popular orbit. So with, for instance, geostationary orbit, probably our answer is probably we can probe until something like a few or several microaxial diameter, which actually have a candidates more than 10. So I believe there are many technological challenges, but if we want to go with hunting many black holes, maybe a good option is the space. So here's the summary. I will stop here. Thank you for listening.
So we have gone about the time, so let's keep on the question part. Kazu will be around for the afternoon, so you are welcome to talk to him directly.
So the second talk is a Blackboard talk, so feel free to make
Excuse me.
Here, big one at chocolate racer though, not a.
Oh, there is.
Go ahead, Mike.
No, so I think that actually some sources already have some things which says
Okay, so we're very happy to have Robert Penna visiting us. Bob was a student of Ramesh in astrophysics, and now he's a postdoc in theoretical physics at Columbia University. And he will tell us about characters of sphere diffeomorphism.
Okay, thanks very much. Let me start by explaining the words in the title, and then I will say a few words of motivation. So here's the setting. If you have a Lie group G, so some symmetry group in physics, like a rotation group, an important problem is to understand its representations. So a representation of a group is a vector space, together with a map from G into the group of linear operators on the vector space. And so it's a way of taking some abstractly presented group and realizing it concretely as matrices acting on a vector space. And if you have a representation, you can compute the character of the representation, which is a function from the Lie group you started with to the complex numbers. And the way it works is like this, character of the representation. To evaluate it at some Lie group element G, some G in the Lie group, here's what you do. You take rho of G, which you can think of as a matrix, and then you take the trace. And the character is nice because it encodes a lot of information about the representation in a nice compact formula. And furthermore, representations can be difficult to construct directly, but we have shortcuts. There's a lot of formulas that let you compute the that let you go straight to the characters and compute the characters without having to construct the representations. And so let me just give you an example of how this works. As an example, take the rotation group of three-dimensional space, SO3. This is a three-dimensional Lie group. And it has a discrete infinite series of irreducible representations. So these are representations that can be broken down into smaller ones. And it has an infinite discrete series of these. So these are vector spaces VL, where L can be 0, 1, 2, and so on. And the dimension of the Lth representation is 2L plus 1. So in physics, these are the Hilbert spaces of a spinning particle. So you know a particle with spin 1 in units of h bar has 3 states, up, 0, or down, and so on. And the characters of these representations look like this. So the character of the Lth representation is a function on SO3. So let's evaluate it at the element that describes rotation about the z-axis, the choice of axis doesn't actually matter, by some angle theta. So the character, in this case, is e to the minus L theta plus e to the minus L plus 1 theta plus dot 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 up to e to the L theta. So even if you didn't know anything about SO3 representation theory and somebody had a way of just handing you this character formula, you could learn a lot. So by plugging in theta equals 0, you'd get you'd find the dimension of the representation is 2L plus 1. And by looking at the coefficients, you could learn the multiplicities of the different states, and by looking at these L's and how they vary, you can learn how the states are organized. So you'd learn a lot if you could just get this formula. And so SO3 is a three-dimensional Lie group. The subject of this talk is an infinite dimensional Lie group. So I'm going to be interested in the group G equals, it's called S diff of S2. And I'll explain what it is and then why I'm interested in it. So this is the group of area-preserving diffeomorphisms of the two-sphere. A diffeomorphism, so if I was just talking about diff S2, a diffeomorphism is a as a smooth invertible map from this two-sphere to itself. So I'm considering the set of all smooth invertible maps. And then the S here tells me that these maps are area preserving. And a reason you might be interested in this guy, well, there's two reasons. One is that it shows up in fluid dynamics. So if you consider the incompressible Euler equations on the two-sphere, so say as a model of the ocean, then this group acts as symmetries. And so there's a very classical thing called Kelvin's circulation theorem that says incompressible Euler on the two-sphere has an infinite number of conserved quantities. And those are come from Noether's theorem in this underlying S diff S2 symmetry. A second reason you might be interested in this group is it shows up in more recent years in the theory of symmetries at null surfaces in GR, in general relativity. For example, at event horizons. So there was just a recent paper from a month or so ago by Anna Flanagan and collaborators, but Laura Donay has written similar, some similar things. Actually, what the story is here is, you know, hopefully if you've heard in this group that there's infinite dimensional asymptotic symmetries at null infinity. You can look at some null surface inside space-time, like an event horizon, and look for symmetries that preserve the structure of the metric near the null surfaces, and you find infinite dimensional symmetry groups. The group you find depends on the boundary conditions you assume near the null surface. So different groups right now have different ideas of what's going on. It's an active area of research. But with some boundary conditions, you find groups like this. What Flanagan and similar papers actually find is an even bigger group than S diff of S2, but this is a subgroup of it, and it's a very important subgroup of it. And I'll take your question in 1 second. What they actually find is a semi-direct product. So you could understand the representation theory of that semi-direct product using the theory of induced representations, which tells you to study little groups, and this shows up as a little group. So it's a good first step to understanding the full thing that they found. So is there a question?
Just what are the infinite conserved charges in the case of the hydrodynamics? Euler's equation?
Yeah, so Kelvin's circulation theorem tells you that if you have an incompressible fluid flow, and it doesn't just have to be on the two-sphere, you can pick a loop, an arbitrary curve in your fluid, and you can integrate the velocity field of the fluid along that curve. And as the fluid evolves, that curve will be vectored along and stretched out and sheared, but this integral will be conserved. And there's an infinite number of these because you can choose any loop. And so that's Kelvin's circulation theorem. And there's a way of understanding this theorem as the conserved quantities that Noether's theorem gives you for this symmetry that acts on the fluid equations, which is in that context called particle relabeling symmetry. And it's sort of an infinite dimensional generalization of translation invariance. It has to do with the fact that the fluid Hamiltonian depends on the momenta of the fluid, but not their spatial labels. So it's like having a free particle where the Hamiltonian doesn't care, has translation invariance, but now you have this sort of infinite dimensional translation invariance. Yeah.
So these are all area preserving that you put it, right? All these infinite.
That's right. So this is an infinite dimensional group, and Noether's theorem, when you have a system with this as symmetries, gives you an infinite number of conserved charges, and you can understand these charges that way.
So can you generalize it to three-dimensional, like air instead of area, like a volume preserving?
Yes, you can. Yes. So, but for today's talk, I'm going to talk about this group. But there's a story of what I just said goes through in 3 dimensions as well. Okay. So, what I would like to understand today are the analog of this formula, these characters, which this formula is for SO3, for this, what do those look like for this group? And so these motivational examples I gave are very classical, but you could contemplate a quantum version of either one of these. And then if you wanted to know how the quantum states were organized, or you wanted to count microstates, you could do that with formulas like this. Okay, so what I could do, if I wanted to just work directly, is start trying to construct representations and figure out how to take traces. But that's a formidable problem for S-diff of S2. So the first thing I want to do to help out is introduce something called the orbit method, which is a result in mathematics that tells you that if you're given any Lie group G, that irreducible representations of G are in one-to-one correspondence with another kind of object called coadjoint orbits of G. And I'll tell you what those are. And in fact, not all coadjoint orbits, but there's a technical condition that they have to be integral coadjoint orbits. And I'll give an example of how this works. Before I explain the correspondence, I'm going to use the fact that just about 3 years ago, Boris Kessin and his collaborators at the University of Toronto completely classified the coadjoint orbits of S-diff S2. So the fact that that classification just appeared at around the same time this is showing up as symmetries in GR made it a natural time to start to contemplate characters of S-diff of S2. And so I'll briefly comment on these things as I go along. Okay, so let me tell you what a coadjoint orbit is. What are the things on the right-hand side of this correspondence? So I'll give you an abstract definition, and then I'll just give you some example. And so if you have let's step back for a second. If you just have a Lie group G.
Sorry, where did the incompressible condition come from your point of view?
From
The
this
error
point of view,
preserving.
So
Yeah.
if I'm using the incompressible Euler equations, then one of the equations is the constraint that the velocity, incompressible means that the velocity field of the fluid is divergence free. And so, the space of divergence free vector fields is the Lie algebra of this group. So the incompressible means that I'm interested in divergence free vector fields, and that corresponds to thinking about area preserving diffs. Yeah. That's why it shows up in this. So there's an analog of this for the compressible Euler equations where the full diffeomorphism group appears. But it's because I'm thinking about divergence free. Okay, so stepping back, what is a coadjoint orbit? So if G is a Lie group, it has a Lie algebra, G, which is the tangent space of G at the identity. The Lie algebra is a vector space, so it has a dual space, curly G star, which is the space of linear functionals on the Lie algebra, just like in a normal linear algebra class. G acts on its Lie algebra by the adjoint representation, and it acts on the dual by what's called the coadjoint representation. So G acts on curly G star by the coadjoint representation, it's called, or the coadjoint action. And as a result, I can study orbits of this action. So here's what an orbit looks like. So this is the coadjoint orbits. And I'll make this more concrete in a second. So fix some element of the dual of the Lie algebra. Then you can study the orbit passing through that element. It's just the space of all things of the form G dot U, where G runs over the Lie group, and this dot is the coadjoint action. Okay, this looks like some very abstract thing, but here's what happens. If you start to work these orbits out for different Lie groups, you find some interesting and surprising things. One is that these turn out to always be even-dimensional manifolds, which isn't obvious from the definition. And in fact, they're very special even-dimensional manifolds. They're always symplectic manifolds. So symplectic manifolds are the things that serve as phase spaces in classical mechanics. So in like the simplest example of a free particle, which is described by position and momentum, its phase space is the space of possible position and momentum. This is always even-dimensional, and it's in fact a symplectic manifold, which makes it extra special and lets you define Hamilton's equations. So these are always symplectic manifolds. So you can think of coadjoint orbits as the classical phase spaces associated in a Lie group. And it turns out that the integral ones are in one-to-one correspondence with the irreducible representation. So physically, if you think of these as the Hilbert spaces of the group, every Hilbert space is in one-to-one correspondence with one of these symplectic manifolds. It's a classical version of the Hilbert space. So this is already useful as a way to organize, to think geometrically about how the Hilbert spaces are organized. But it lets you do more. So it turns out all the data on one side of the correspondence has an analog on the other side. So that characters on the representation theory side can be computed entirely with data on the coadjuvant orbit side. I'll give you the formula. Let me say a word about where the formula comes from. So you can think of a character, which I erased, as a kind of partition function, taking some trace of an operator. On the orbit side, it becomes an integral over the coadjuvant orbit. It becomes a path integral. You can think of it as a path integral on the corresponding classical phase space, an integral over the space of all classical states with some weighting. And so by computing path integrals on coadjuvant orbits, you reproduce the characters. And in cases of infinite dimensional Lie groups like S div S2, this can be the best way to, or the easiest way forward. Furthermore, the path integrals that you have to compute would be hard to compute for S diff S2, because in this case the coadjuvant orbits are infinite dimensional manifolds. It would be very hard to set up the measure. But we know when we see like integrals like path integrals, a good way to get at them is to use the method of stationary phase. It turns out that for the path integrals that arise in the orbit method, when you want to compute characters as integrals over these classical phase spaces, the integrals localize exactly. And so there are formulas that let you compute the character directly by studying some fixed points of something on the orbit. I'm going to give you the formula for how that works. It's called the Atiyah-Bott fixed point formula. And then I'll try to quickly mention how it works for SO3 and sketch what happens for S diff S2. Fixed point formula. But I know I just said a lot really fast. So is there a question at this point?
Actually, Bob.
Yeah.
I'm missing a motivation.
Okay.
Why are we studying all of this?
Why are we studying?
Where do you hope to end?
Yeah. So if you had a quantum system with this symmetry, so you can imagine like a superfluid. There are papers on superfluids where this group appears. Or if you imagined some quantum version of event horizons, then once you had this formula, like the one I wrote down for SO3, you could, for example, you would have a good understanding of the Hilbert spaces of those systems. So quantum mechanically, you know for a spinning particle, all I have to tell you is its spin is L, and then I know there's 2L plus 1 states, and I know how the states vary, and in this given state I know that there's a single state with each spin. I want to contemplate if there was a quantum version of either of these systems. I want to be able to tell you those sorts of things. Here's the parameters you have. To fix a state, you have to give me this list of parameters. They will occur with these multiplicities, and yeah.
So
those sorts of
this
things.
whole
You can
program,
even count states.
this whole program is a way to go from some classical problem to a quantum equivalent. Is that the idea?
That's right. Yeah.
Maybe it's worth mentioning there's a simpler example, which is ADS3 gravity. So if you look at all the phase space of solutions to ADS3 gravity, they form cojoint orbits of the Virasoro. And
so for ADS3 gravity, where the asymptotic symmetry group is 2 copies of Virasoro, Virasoro has the Virasoro group is a central extension of the group of diffeomorphisms of the circle. And it's a central extension of this. And the representation theory of the Virasoro group is extremely rich. Conformal field theory and string theory and ADS CFT all have a lot to do with the representation theory of this group. It'll turn out that the representation theory of this guy is not as rich, but it's a natural generalization of the group of diffeomorphisms in the circle. People have gotten a huge amount of mileage out of studying Virasoro representation theory, and so this is sort of a natural thing to contemplate.
But there's no central extension of it, right?
So there is actually a central extension. There's something called the Lick-Nirowich cocycle, and when you can study an analog of Euler equations on the extension, and it has to do with magnetized Euler equations. So the central charge has to do with the magnetic field that the fluid is flowing through. There's something called the Lick-Nirowich cocycle. I don't know that it's as rich. It's not as rich of a theory though. I mean, it doesn't seem. Yeah, I don't know where it leads, but there is something. Lick-Nirowich cocycle. Okay. Okay. So this formula will just basically, so this is the formula we can use to get the answer we want, and I tried to motivate it by thinking of, we're computing, characters are like partition functions, which you can think of as path integrals on these classical phase spaces, and it turns out those integrals localize to their fixed points. And so let me just tell you the result. So if I want to compute the character attached to some coadjoint orbit O, which I can think of as corresponding to some representation rho, then that's a function on the Lie group. And I'm going to write Lie group elements in this funny way as q to the v hat. So earlier I talked about a character for SO3, and it was evaluated at elements of the rotation group, things that look like gz of theta, or rotation about the z-axis by theta. I'm going to write that as q to the v hat, where q is e to the I theta, and v you can think is the infinitesimal generator of rotations, and v hat just differs by v by there's this factor of I that I put here. So you can think of this as the same thing as this rotation generator. And if you wanted to compute its character using the fixed point formulas, here's what you would do. Instead of taking a trace of a matrix, you think of v as a vector field on the orbit, on a coadjoint orbit that you're interested in, and you study its fixed points. Let me tell you what that looks like, and then I'll go further. Let me tell you what that looks like for SO3. So, for SO3, the Lie algebra is isomorphic to R3, and so is the dual, and in fact, you don't have to really distinguish the Lie algebra from the dual for SO3. So, for SO3, what do the coadjoint orbits look like? So in that case, we can just work on working on R3, and it turns out the coadjoint orbits. I'm going to give these axes labels with J, because I can think of this R3 as a space of angular momentum of the spinning particle. The coadjoint orbits are two spheres. I can call this two sphere O sub j, where j is the radius of the two sphere. And the integral coadjoint orbits, this is a technical condition, which I don't have time to explain. This condition, however, picks out the orbits with j, with radius, with size j equals to L plus a half. L can be 0, 1, 2, da 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 da. So two spheres are even dimensional. In fact, they're symplectic manifolds. You can think of this two sphere with size j as the space of classical states of a spinning particle with angular momentum j. And there's, of course, a continuum of two spheres of different radii, but these integral ones are in one-to-one correspondence with the representations. So the two spheres of bigger and bigger sizes, these bigger and bigger two spheres, are the things classically that correspond to the Hilbert spaces of larger and larger dimension. And so the area of this guy is the dimension of the corresponding Hilbert space. And so to get characters of SO3, using the fixed point formula, if I want to understand the character of this rotation generator, I think of the infinitesimal generator, this d by d phi, as a vector field on the two sphere. So it's the thing that swirls around like this, and I study its fixed points, or its zeros, which for a two sphere are these two guys. And so I get two terms, and each term is weighted by something called q to the h, where h in this example turns out to be j plus a half, so it's just the value of the angular momentum at the fixed point, plus or minus, depending on whether I'm at the north or south pole. And then there's another factor here, 1 over 1 minus q. And this looks different from what I wrote earlier when I wrote down the characters as a sum of a bunch of terms. But if you expand this out, if you take your contributions for your two fixed points and you expand this out using 1 plus q plus da 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 da, you'll recover the thing I wrote down earlier. And so this is an example of how you can get characters just using data on the orbit. And in the last minutes of the talk, I want to sketch how this works for S diff of S2. Yeah, is there a question about this? Because again, I'm saying a lot very fast. So you have, so SO3 has these coadjuvant orbits, which are two spheres. You can think of this as a classical phase space of a spinning particle with spin J. And these classical phase spaces are in 1-1 corresponds with the Hilbert space of a spinning particle with spin J. And furthermore, you can think of group elements, when you want to compute their characters, correspond to vector fields on these spheres. In studying the zeros of those vector fields and how things act near the zeros of the vector fields, it turns out there's a formula that just lets you jump to the characters. So this is totally geometrical data for this thing that I started out with looked very algebraic. And so in some cases this is the best way to compute the characters.
When you go to the poles, then you have to go down, right? Because then there is not any circle to get around.
I'm sorry?
Confused. Because you're going to consider the vector fields in this direction, which is the phi direction, right?
Yeah, that's right.
But when you go to the pole, there is not any phi direction left. It's just the circle associated with
So this vector field that I'm considering is vanishing at the poles. Right. And the fact that it's vanishing there, the T-Abad formula says study the fixed points, or the zeros of the vector field, the fixed points of the diffeo corresponding to the vector field. And it says at those fixed points, put this data, Q to the H, where if this is some symmetry, this is the corresponding Noether charge up to some factor, up to some constant, times, and it tells you what to put here, and it's all in terms of data on the orbit. I actually didn't explain what this would be in general. Let me say a quick word about that. In order to apply the formula in the version I've used it, the coadjuvant orbit actually has to be a complex manifold, which means that it has complex coordinates, z bar. And to use the formula, you have to take your vector field, this is v equals d by d phi, and you have to go very near the fixed point and write it in holomorphic coordinates, z by dz, and you read off the coefficient here, and that coefficient shows up in the exponent here. So this is a recipe I'm giving you. Okay, let me just sketch now, in the last minute or two, some changes you have to make for S diff of S2. Okay, so let's now go to our main example, S diff of S2. So here's G. Its Lie algebra is the group of divergence-free vector fields on the two-sphere. And what's the dual of this Lie algebra? So the dual of a vector field is a one-form field. So you can think of this as a space of one-forms on the two-sphere. But because these are divergence-free, we actually identify one-forms that differ by an exact form. And this quotient is the analog on this side of the divergence-free condition here. And then you can study the coadjoint action of G on G star. So if I have G in the Lie group and some one form, or really a coset, in the dual of the Lie algebra, then the coadjoint action, G dot U, well, G is a diffeomorphism, this is a one form. It turns out, when you compute it, it just acts by push forward. Alright, that's the coadjoint action. You can study orbits of this action, and as I mentioned earlier, there's this recent work from 3 years ago by Kessin, motivated by problems in fluid dynamics, gave a complete classification of the coadjoint orbits. And so, in the SO3 case, the orbits were two spheres labeled by a single parameter J, which was the angular momenta. Now there's actually an infinite number of parameters that label the orbits. So the analog of J, the size of the two-sphere, is called the entropy. Ik of U. And there's an infinite number of these entrophies. They can be 1, 2, 3, 4, da 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 da. And the way to compute the entropy at some point on the orbit is to take U, which is a one form, take its exterior derivative, which is a two form, divide by the area form, which gives you a function, take some kth power of that function, and integrate the function over the orbit. Okay, these were actually known from fluid dynamics, where they're called entrophies, and they were known to be conserved by the Euler equations. And it turns out, modulo a caveat that I don't have time to explain, these completely label the orbits. So just as before, for SO3, the orbits were two spheres labeled by their radii. Now you have an infinite number of parameters that you need to tell me to pick out an orbit. Once we're on an orbit, we can compute its character using the fixed point formula. How much do I want to say about this? So for example, we could compute the character q to the v hat, where let's take v to be the generator of rotations. That's certainly a divergence-free vector field on the sphere. And we can use the Atiyah formula to get the answer. Let me just make some remarks about what happens, and then I'll stop. So just as before, you had this thing h up here. For this, h will be the total angular momentum of the fluid. So h will be, so this is the Noether charge corresponding to this symmetry. So if the fluid's velocity is, you think of u as the fluid's 3 velocity, then u sub phi integrated over the 2 sphere is the total angular momentum carried by the fluid. Plus there's a constant here. That'll be the h for this example. And another thing you needed to know in this formula was you had to have a complex structure on the orbit. So the 2 sphere is a Riemann sphere, so it's obviously a complex manifold that I can give holomorphic coordinates to. It's not so obvious that the orbits arising over here have a complex structure, but here's how you can see it. So if you go back to the Lie, and this is the last thing I'll say, and then I'll stop. If you go back to the Lie algebra, the divergence-free vector fields on S2, you can expand this guy in a basis. So if you take axial m to be n cross grad ylm. So n here is the normal to the 2 sphere. YLM are ordinary spherical harmonics. So this is n cross the gradient of a spherical harmonic. This guy is a divergence-free vector field. All divergence-free vector fields can be expanded in this basis. So it's a basis for this guy. And now if I go to my say this is some coadjoint orbit, and I'm studying its fixed point, so I'm sitting very near a fixed point, say u0, I can move around the orbit in different directions by acting with XCLMs using the coadjoint action. So XCLM might move me over here, XCLM prime might move me in this direction. So these XCLMs give you coordinates, an infinite set of coordinates on the orbit. The guys with m equals 0 act trivially, so those are not coordinates, but it turns out that the guys with XCLM with positive m act like holomorphic coordinates, and the guys with XCLM with m less than 0 act like anti-holomorphic coordinates. And so you could write this vector field, d by d phi. You could think of this as a vector field on the orbit, where it would look like m XCLM d by d XCLM. And you could read off these coefficients, and you'd get an analog of this factor, but now with a product over m's, things weighted by 1 minus q to the m. So the upshot is all the pieces are there, and you can indeed compute characters of for this bigger group and start to think about it quantum mechanically. And the best way that I know to actually do it is by recasting what looks like this very algebraic quantum problem in this very geometric classical looking language. And again, physical applications still TBD, but I tried to say at the beginning that this does show up in natural systems like event horizons and fluid dynamics. And so if you were to contemplate quantum versions of those things, and you just want to understand their Hilbert spaces and how the states are organized, and if you want to try to count microstates in the representations with different properties, these formulas let you read that off. Yeah, and so hopefully along the way you learned something about the orbit method. It's just this neat thing that lets you understand representation theory geometrically, and hopefully this Atiyah formula is very nice. That lets you compute characters geometrically. So if nothing else, those two things are useful tools just to have, just to be aware that they're out there. Yeah. Okay.
Question for
So
do you have a target? I mean, is there something where you know what the answer should be that you can compare when you finally get this?
Yeah, so one way to kind of check the answer is S div S2, it turns out can be approximated by SUN in the large N limit in a certain precise sense. And so you can, the characters that appear, you can sort of view as a large N limit of SUN characters. And the way that goes is, I mentioned you have this basis in terms of spherical harmonics. If you say so this Lie algebra has this basis, and so you have all these like CLMs, where this is normal L and M that show up in this various spherical harmonics. And so L here can run up to infinity, but if I say I want to consider a truncated version of this story, where I throw away everything with some large L, and I only keep things with L less than N, for some cutoff N, then I'll throw away everything except N squared minus 1 spherical harmonics. I'll only have N squared minus 1 CLMs left over. That's the dimension of SUN. And it turns out that, in a certain sense, you can view the thing that's left over as SUN, and it's not exactly SUN. You have to deform it a little bit with a deformation that goes to 0 in the large N limit. But yes, so the best way I know to check that these formulas aren't totally crazy that you get, is to look at SUN formulas in the large N limit.
No, I apologize. I sort of meant comparing it against a physical situation. Is there a black hole event horizon where you know what the time should be?
That's also an interesting question. But yeah, so no, I don't know of one. No.
Okay, I'm afraid we have people have obligation here. Thank you so much for your talk.
Please, all the BHI postdocs come to me.
That's okay. Yeah, I know.
Yeah, it's always the case because 30 minutes is so short.
It's so hard to explain anything, especially in the second one. Yeah.
No, I think we did a very good job.
I looked at your paper. It's a very nice piece of math. You talk about the entropy at the end, though, but you know, like, this information in the characters will never tell you anything about entropy. It's like all the information about the Hilbert space orthogonal to that.
I know.
It's the exact opposite.
Yeah, I'm gonna probably remove those marks from the rest of the next draft.
Yeah, I think they're a little wrong because like in the Virasoro story, the Hilbert space decomposes into these Fermat modules.
Yeah.
And the characters just tell you about an individual Fermat module.
Yeah.
But the entropy comes from the degeneracy of the Fermat.
In other words, these are just very useful representations.
Yeah, so this is like kinematic information.
Yeah.
But the actual things like the entropy are kind of like physics.
Yeah, I know. Yeah. So yeah.